This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. Did I still have anyone's paper? Did I have your mid-semester test paper? I think that one. Is that right? Yep, thanks. Okay, so let's get started again. So where were we? It might help if I projected the right screen. Oh, no. Someone's going to fall asleep if I do that. No, is that all right? Should I leave the lighting like that? Yeah. Sorry? Yeah? Okay. No problem. Yeah? Okay. So if you remember last week, we were talking about strange things like water waves and measuring things on piers and but we got through some interesting aspects about our hearing, things like the masking effect and this issue of directionality for different frequencies. And we stopped just short of looking at how these tools are used in actual perceptual audio coders. So perceptual audio coders or psychoacoustic coders are those that take advantage of this psychoacoustic masking. And all the modern, efficient audio coders, such as those you see listed there, are based on this technique. So I didn't want to go. I won't go in as much detail as I did in the video coders, but I just wanted to talk about the evolution of these coding systems so that we understand where the tools came from and why they're used, where they're used, and how the technology has evolved over time. Then we'll finish up by talking about, finish up on audio, talking about these parametric coding methods. I won't bother introducing that until we get there. Then my plan is, that should take about an hour, and then maybe we'll have a break then. Then I'd like to talk a little bit about the expectations for the project report. Particularly, I'd like you to see that before you take the break, for those who want to spend some time on it. And then we'll be able to start the next topic, which is multimedia transport. So the sort of logic is that we've now, when we finish with the audio coding, we know what signals we need to carry and we know how they behave. So let's start looking at how we can actually transport them over different networks and what happens when we lose bits or have errors or something like that. Okay, so the first audio coder that used the psychoacoustic masking effect that we talked about last week was actually MPEG-1 audio. It's called MPEG-1 audio. And so it, of course, was part of the MPEG-1 initiative in the International Standardization Organization. And so while the MPEG-1 video group was off defining video compression systems, there was an audio group who were looking at efficient ways of encoding high-quality audio to be associated with the video. And they defined their coder as 3 layers of complexity. Complexity and efficiency. I'm just thinking on the top of my head, you could almost see this as being analogous to the profiles and levels type of thing. It was trading off the complexity for the performance. So there were 3 layers defined, not layers in the sense of scalable coding where you can build on top of one another, but more in terms of increasing complexity. And there were 3 layers, and we'll look at how the parameters were different for these different layers that were defined, with the anticipation that maybe we want a standard for audio coding that's very simple. So not necessarily really good efficiency, not really low rates, but we want to keep it simple. So that was this MPEG-1 layer 1. And as I've discussed with regard to standards before, it's very hard to, if you're in a group defining a standard that you hope will be used for generations to come, to get exactly the right spot in terms of complexity, in terms of performance and so on. So in the end, this MPEG-1 layer 1 was never used. It was just so simple that with the progression of processing power and memory costs and so on, it was just as easy to go to the next one along. As I say, well, I'll talk about what's actually in these coders in a second. The MPEG-1 layer 2, though, was very successful and was adopted quite early for broadcasting. So MPEG-1 layer 2 is still broadcast, in fact, on our digital TV services here. The audio track that's associated with the video is MPEG-1 layer 2. Then there was a much more complex solution, the MPEG-1 layer 3, which was unused for quite a long time, for many years, because it was just too complex. And then all of a sudden, I'm guessing around the late 1990s, the processing power available in a PC exceeded a threshold, and all of a sudden you could do it all in software, and this became MP3. So a lot of people assume that MP3 stands for MPEG-3. Now that you know there is no such thing as MPEG-3, and in fact it's MP3 is MPEG-1 layer 3. These coders were dual channel, so intended for one or two channels, so they could operate in mono mode with just one channel, and they could operate with 2 channels in a couple of different modes. So as you see, this dual channel, what they call the dual channel mode, don't bother memorizing what these names mean, but the dual channel mode was dividing the available bitrate into 2, and you just code the 2 channels completely independently. In the stereo, what's called the stereo mode, you have a budget of a total number of bits. You code the channels independently, but you can allocate bits across them, sort of trade them off. So at one instant you've got I don't know, 60 kilobits per second for one channel and 80 kilobits for the other, and then a little bit later you swap it so that they're equal, and so on. Just depends on the demands of the different channels. And but they're still coded independently. It's only the bitrate that's being allocated to them in some sort of coordinated way. And then this joint stereo mode is actually looking for correlations between the 2 channels. Okay, so what's the form of the codec? It's a psychoacoustic model-based coder. As we've described, it just this MPEG-1 layer 1 just had 32 channels from the filter. So if you remember, let me go back to this model that we had of a psychoacoustic coder. I'm sure we had one. right? So remember, the idea of the psychoacoustic coder was that we process our audio in frequency channels, and because of the different sensitivity to different frequencies, and because of the masking of some frequencies by other frequencies, then we can quantize them and allocate bits according to that channel based on a psychoacoustic model that again is frequency based. So in the case of the frequency-based decomposition for this MPEG-1 layer 1, there were 32 channels defined, and no attempt to do any temporal masking, exploit any temporal masking. It was just split a input number of samples across 32 channels, and look at the simultaneous masking across, or frequency masking that occurs between them. It's hard to be very definitive about quality and bit rates, particularly for the reasons I've described before with regard to video, that it depends on which MPEG-1 layer 1 coder we're talking about. But roughly speaking, you could get what people would consider almost indistinguishable from CD quality at around 384 kilobits per second. It's not a figure, certainly don't bother memorizing it. I just want to give you a feel for what sort of performance this achieved compared with the others. So with layer 2, still 32 channels were obtained from the filter, but the main feature of this one is that processing was done across 3 frames in sequence, in time. So now we could do temporal masking as well. So when that masking effect occurred, it has a sustained effect for some tens of milliseconds, if you remember, after the masker has ceased, and so we get greater efficiency. And so the CD quality reference is achieved at around 200 kilobits per second, more or less, in this model. Then with MPEG-1 layer 3, there's an extra transform carried out. So for each of the outputs of these channels, it then goes through this other transform. This MDCT is a modified DCT. We won't worry about the details of what the filter does, but it's think of it as another frequency decomposition, like a Fourier transform or like a discrete cosine transform. So it's got frequency and temporal masking, and it's got much finer frequency resolution as a result of these two stages of frequency decomposition. It adds Huffman coding, it can do variable rate, and gets that bit rate down for what we call CD quality down to around 112 to 128 kilobits per second, more or less. And that of course became known as MP3 and is still widely used, of course. You still get internet radio channels that are MP3 coded. So what happened with, I said this was going to be a little bit of a history lesson. What happened with audio when the MPEG group got back and started working on MPEG-2? Well, at this point they thought, well, we've got this efficient stereo audio coder. What's missing? Well, maybe we should do surround sound. So they started working on this MPEG-2 BC, meaning backwards compatible audio coder. So that whereas the MPEG-1 was stereo channels, or 2 channels, this MPEG-2 one would be 5 channels, or 5 channels plus the low frequency effects channel, so the 5.1, remember we talked about that. And they extended some sampling rates, but the main aim was to make a surround sound coder that was backwards compatible. Backwards compatible in the sense that that we could, if we had an MPEG-1 stereo encoder, it could be decoded by an MPEG-2 surround channel. Did I say that around the right way? An MPEG-1 stereo encoder could be decoded by an MPEG-2 surround sound decoder, or vice versa. So all the combinations were possible. And that sounds like a good idea if you in isolation of everything else that's going on. You might think, well, that's probably a good idea because we've got these MPEG-1 audio coders out there already. This provides compatibility between the two. Good idea. The only thing is, it basically didn't work very well. And it didn't work very well just because of those constraints of trying to make it backwards compatible. And it may still have been okay, but there was another serious contender in the audio coding space that came out about the same time. Any guesses about who that might be, or what that might have been? It's all right. Might not have expected you to, but I shall reveal all in a minute. So this is how the backwards compatible was supposed to work, and indeed it did work. It just meant that, as I said, by insisting that we make the two main front left and front right channels compatible with MPEG-1, it meant you couldn't get as much coding efficiency as if you didn't apply that constraint. But this was the way it was intended to work. You had the 5 channels in. You could encode these two main channels as an MPEG-1 stereo pair. Then there's the extension coder. Then, of course, a directly aligned decoder could take those channels and reconstruct the surround sound. But also, we would be able to pull off just the 2 main channels if we only had an MPEG-1 decoder. MPEG-1 encoder could talk to MPEG-1 encoder could talk to MPEG-1 decoder, of course. But MPEG-1 encoder could also talk to a full decoder in which some material in these surround channels would be synthesized essentially from the combined signal. But it was Dolby who entered the audio coding space at the time. They came out with Dolby Digital from the cinema, and we'll talk about digital cinema maybe even the very last lecture of the semester, I think. But anyway, briefly, Dolby had been big in the cinema, in analog cinema sound for a long time, but around the early 1990s, they developed Dolby Digital, and the motivation for the efficiency of this encoder was that they only had a limited bit rate available, 320 kilobits per second. We'll look at where that came from, but essentially it's real estate on the film, because they wanted to include the Dolby Digital data somewhere on the film strip, a physical film strip, along with the movie itself, of course, and also the analog audio channels. So there wasn't much space. So without going through all the details of where the space came from and how fine you could make the optical print on the film to represent your digital data, the bottom line was that they ended up with 320 kilobits per second. And so they developed this surround sound digital encoder and decoder system that gave very good quality at this 320 kilobits per second. Of course, they weren't worried about trying to make things backwards compatible, so they had more freedom than the MPEG group. So once it was developed and available for cinema, it was also adopted widely in digital TV broadcasting and DVD videos. They commonly use Dolby Digital as well. I mentioned MPEG-2 or MPEG-1 Layer 2 with regard to digital TV broadcasting. In fact, they're both used. So it's what about the Dolby encoder? It's a perceptual encoder, so it uses psychoacoustic masking like the MPEG-1 Layer 1, Layer 2, Layer 3. But the channels are coded independently. There's no backwards compatibility constraint. One of the reasons they got higher efficiency was that they used an adaptive filter. So whereas the MPEG-1 filters were, let's just use this one, had this fixed length, fixed number of channels, fixed length frame of 12 samples. The Dolby one adapted that length. Now the reason that that is useful is that it depends on whether the signal, you would know this from your Fourier theory, if the sound that we're wanting to encode is reasonably stationary, is reasonably unchanging over some period of time, then you could use a long filter and you would get very fine frequency resolution, right? When you've got a certain number of sample points in time, you've got the same number of frequency channels when you convert to the frequency domain. So you could get very good frequency resolution, and so you could get a very good model of the masking of these different frequencies. But then other parts of the music, it might be highly dynamic, so it's I don't know, crash cymbals or something that's changing very rapidly rather than having long periodic notes. And so they could adapt then to have a shorter filter, which gives poor frequency resolution but good time resolution. Okay, able to change rapidly. So the result was that the coder was very efficient. They used coupling. Remember, the coupling was the name given to processing the high frequencies in, well, does anyone remember? How do we process the high frequencies efficiently? Encode the high frequencies efficiently? We used the term coupling, didn't we? Yeah. No, I just can't remember. I was studying last week's lecture last night, but I just can't remember. That was the observation that for very high frequencies we can recognise the direction from which the sounds come, but only by the magnitude, not the phase, right? So that means that for high frequencies we can filter off those high frequencies from all 5 channels, encode the signal just once, but then include some side information about how high a magnitude or amplitude we need in each of the 5 channels. Yeah. So above about 10 kilohertz, roughly, we save a lot of bits because we only need to encode once with some side information. One of the other reasons, just from a practical point of view, why Dolby was highly successful is that it was quite easy to get a 2-channel version of their surround sound audio, because cinemas had been largely set up to support just stereo. So they could provide a single copy of the film print, and of course if your cinema was only set up for analog audio, it could read the analog audio that was still provided on the film strip. But even if you just bought the Dolby digital decoder but didn't have all the surround speakers and amplifiers and so on, you could still get a good quality stereo reproduction. So what do you think the MPEG-2 group did when they saw that this was coming out? They called everyone back in the room and said, okay guys, back to the drawing board, we need a better audio coder. And that's actually where the MPEG-2 AAC, Advanced Audio Coding system, came from. It's could be seen as MPEG's counterattack. They would put it more politely, but that's effectively what they did. They didn't want Dolby to take over the world. They wanted an open standard, and so they wanted a more efficient solution. So they threw away the backwards compatible thing and tried to come up with an audio coder that was more efficient than Dolby, essentially. And indeed they did so. You'd be familiar with AAC if you just use iTunes or something like that, right? Apple uses AAC. Okay. So this MPEG-2 AAC coder was intended to be more flexible than the earlier ones. Lots of combinations of channels, as you can read there, a large range of sampling rates, and around 30% fewer bits than MP3, so 2 channels at less than 96 kilobits per second instead of about 128 kilobits per second, roughly speaking. What was MPEG-2 AAC based on? Well, it used longer long filters and shorter short filters, so it was doing adaptive filtering as I described that Dolby was doing. Used a different filter. What else? So, and where there was quantization noise, it was managing where that appeared not just in frequency but also in time. So if there was going to be masking of quantization noise in time because of the temporal masking, it was taking advantage of that. There was this predictive tool for where there were stationary signals, they could be detected, and there was a predictive component to the encoding. They used their joint stereo coding, so taking advantage of multi-channel coding. It was a combination of techniques. One was the MS stereo coding, so the mid side, remember, we can, if we had left and right stereo pairs, then if the signals were very different, we'd code them as left and right. If the signals were quite similar because there was dialogue, for instance, in the movie, then we would take the sum and the difference, just more decorrelated. And they also introduced this high frequency coding approach. Dolby calls it coupling. MPEG does essentially the same thing, slightly different parameters, but essentially the same thing, and they just give it a different name, intensity stereo coding. AAC has gone on and been developed further with the MPEG-4 initiative. So again, while the MPEG-4 video people were defining their new and very flexible video system, the audio group were extending AAC. There are no fundamentally new coding techniques. Perhaps the perceptual noise substitution is an interesting one. So instead of where part of the signal was detected as noise, then rather than encode that noise, they just synthesized it at the decoder. It was adaptable to code speech more efficiently because it could detect periodicity of voiced speech segments and switched in a long-term predictive coder tool when needed. And also allowed for low delay modes. So the idea was that MPEG-4 could be used for anything. Right? And so if you wanted to use it for low delay applications, such as a conversational service, then they could switch into low delay, less efficient, but low delay mode with things like shorter frame sizes and so on, shorter filter lengths. Okay, so I told you that was going to be a very brief introduction to the development of these standard coders, but I wanted to finish by looking at where even more efficient audio coding has gone after the development and exploitation of these psychoacoustic properties. So, in the same way as we discussed what we could do with video coding if we are running out of bits, we can ask the same question of audio. So if we've got this is how a perceptual coder should operate, or one way of looking at it, where we've got our audio envelope, which is the purple there, and we've got a masking threshold, which is the black line, and we keep all the we don't bother encoding any signal that's below that masking threshold, but we also allow quantization distortion up to that masking threshold. But what happens if we are running out of bits, if we're trying to compress our audio below that sort of 96 kilobits per second or thereabouts for AAC? Well, then inevitably we're going to run into this problem where the quantization noise will increase, it'll exceed the masking threshold, and it will be audible. So it's a bit like the audio equivalent of the blocking artifacts being visible in video when we throw away too many transform coefficients. So something has to be sacrificed. So what could we do? The obvious thing we could do is reduce the bandwidth, right? So instead of coding the entire frequency range, 20 to 20 kilohertz, maybe we, for very low rates, we say, well, look, we have to sacrifice something, so let's low pass filter the signal, and that'll mean that we have a lower bandwidth, we can sample at a lower rate, we have fewer frequencies to try to model in our psychoacoustic coder, and so we'll be able to provide sufficient quantization accuracy that our quantization distortion is kept below this masking threshold. So is this similar to reducing the spatial resolution for video, do you think? One nodding head? Yes. Yeah, that's right. It's the same concept, right? Except that in the audio space we have some more tricks available to us, which is the interesting part. Enough to keep us all awake tonight, I'm sure. Because in the audio space there's high correlation between the high and the low frequencies, particularly for something like music. If what I've shown to you here is the low frequency spectrum, a low frequency part of the spectrum for two quite different musical instruments. And consider that question at the side there. Could you guess something about the missing high frequencies? And I think you probably could, right? We might not know exactly what where these peaks and troughs might be if we revealed the high frequencies, but look, we have these harmonics here, right? And we would expect them to be continued there. Similarly for the flute, right? We would expect these harmonics here. So given this low part of the spectrum, we could guess something about the high part of the spectrum, right? At least at a high level, just looking at that. And indeed, we would be right, right? If I reveal what those high frequencies look like, then those harmonics, those peaks in the spectrum are continued. So we might be able to, even if we don't encode them precisely in terms of a waveform coding approach, we could parametrically describe them perhaps by saying that these high frequencies are can be characterized by peaks at this particular level, for instance. Right? And that's the principle of a coding enhancement called spectral band replication. Pardon? Prediction. Effectively, it's prediction. Yeah, that's right. We use the spectrum of the low frequency spectrum to predict the high frequency spectrum. So it's what I'm describing here is a little bit of magic to get back what we've just lost by filtering out the high frequencies. It's magic because we've lost it, but we can estimate the high frequencies from the low with some parametric assistance. And this coding approach or coding enhancement is highly effective at low bit rates. Of course, if you've got enough bits available, you're better off encoding the whole frequency range. But if you haven't, then you get one approach would be to just low pass filter, but you get a substantial increase in performance if we low pass filter but then do this reconstruction of the high frequencies by some sort of parametric assistance. And as you might guess from the description I've just given you, you can actually use this technique with almost any coder, right? Because we can encode these low frequencies however we want, and then once we recover them at the decoder, we send some parameters to tell us how to estimate what these high frequencies are. So it doesn't matter how these low frequencies were encoded. So there are various coders that use this spectral band replication. Don't bother memorizing coder names, but if you happen to come across them in some of your reading or in your project or whatever, high efficiency AAC is one that uses it, or AAC Plus, that's a trademarked one, or MP3 Pro in the case of using it with MP3. So there are a few different names. So this is what it looks like in block diagram form. In this case, using AAC. So our audio input goes to this spectral band replication encoder, which does the low-pass filtering and just sends the filtered audio to the separate encoder, which happens to be AAC in this case. But it also parametrically describes that high-frequency reconstruction, and that's the ancillary data that's sent that's identified at the top there. And but that ancillary data is only about 1 to 3 kilobits per second per channel, so it doesn't involve a lot of overhead. So then we've got a little bit of extra data that we've multiplexed into the bit stream, but if we pull that off at the decoder, at the receiver, sorry, we use the AAC decoder on the low frequency audio, and then the SBR decoder at the end there uses that ancillary data that parametrically describes the missing tones to reconstruct an approximation of those high frequencies. So it tries to estimate or describe the spectral envelope of the high frequency components without having to actually encode them. And if you think about the fact that we're doing this on the high frequencies, that's consistent with what we learned about our sensitivity to high frequencies, because we're only sensitive to the magnitude anyway, right? So we only actually need the magnitude of our spectral peaks. We don't need the phase relationship, so it works in our favour as well. As you see, also high frequency noise is just estimated and described parametrically rather than trying to encode it all. So looking at some spectral diagrams, pretty poor reproduction, sorry, but this is the only source I could easily find. The output of our encoder is shown here. So this is the AAC encoder. It's encoded only the low frequency components. At the decoder, we use this low frequency data to augment and generate a high frequency version. Then we apply the shaping information, so we end up extending this low pass signal out to something like twice the bandwidth or more, and comparing it with the original, we haven't got all the very high frequencies in this case, but we've been able to approximate this missing part of the spectrum. Does that make sense? Yeah? Okay, so there's one other approach to parametric coding that I'd like to describe, and that's called parametric stereo. And it's a similar motivation in the sense that if we're running out of bits, if we want to compress our audio to a very low bit rate, then maybe we need to sacrifice the number of channels we encode. So if we have a two-channel audio system, but instead of coding both channels, we just encode one channel and just parametrically describe the other one. Right? So we can synthesize effectively the second channel by with parametric assistance. So if we look for things like as described here, the relative phase between the two channels and the intensity differences, and effectively the alignment of the two signals in the two channels, then we can describe those differences, encode one channel, and synthesize the second one. And this is yet another set of, again, this can be used with any encoder. With AAC, it has these various names: AAC Plus version 2, Enhanced AAC Plus. And it can be used beyond just two channels to surround, 5-channel surround, for instance. So there's an MPEG surround specification which uses this. And in this case, we encode just two channels, but synthesize the 5.1 or the 5-channel surround sound. So, how well do these things actually work? These parametric systems. I think this is a highly enlightening diagram. There isn't much data on it, but it shows just how well these things work. So, what this shows is that if we were just encoding our stereo pair, so we've got a original PCM 44.1 kilohertz 16-bit stereo signal, so that's CD quality. That's exactly what comes off a CD. And we encode it using AAC at lower and lower rates, and we've got this perceptual quality, so it's a bit somewhat subjective perhaps, but we put people in controlled audio spaces with headphones, and we tell them, tell us whether this audio clip is better quality than this audio clip, and so on. And we perform lots of magic with statistics and extract a scale that's usable, and it's reproducible, so it's reliable. So we encode that stereo pair at lower and lower bit rate, and we see that AAC performs quite well above about 96 kilobits per second for 2 channels, but below that the perceived quality starts to drop off, as you see. So it's at that point where we say, well, let's do a different trade-off. Let's trade off the full frequency that we're encoding with AAC for the spectral band replication, which is this one. So this is the bit that does low-pass filtering and encodes the high frequencies using that parametric assistance. And you'll see that, of course, the quality continues to decrease as we reduce the bit rate, but it keeps this quality significantly higher than AAC alone. Eventually we get to a point where this AAC Plus version 1, the SBR one, drops off in quality, but AAC Plus version 2, which is the parametric stereo, allows us to sustain higher quality to even lower bit rates. So even getting around to something like 20 kilobits per second, we're able to provide or maintain a reasonably good quality for a stereo audio reproduction. Okay. So I think it's interesting to just consider how the audio solutions have kind of converged. So as we've looked over this brief investigation of audio and speech coding, we've seen at very low rate, very low quality speech coders using vocoders, we've seen improved quality and increasing bit rate to use KELP and AKELP, and then these highly adaptive coders that are defined by the ITU. Remember, I went through the details of them. They switch into KELP mode when they detect voice. They switch into transform coding mode when they detect music and so on. And in the end, they don't get super high quality, but they get acceptable quality at a fairly modest rate of 10 to 20 kilobits per second, adapting between speech and music. And the journey we've just been on has arrived at the same point, but from a different direction. So from very high quality, we haven't talked about SDDS and DTS, but there are other cinema audio systems that we'll meet later on. But MP3, Dolby and AAC have maintained reasonably high quality at ever decreasing rates to the point where we can get AAC Plus version 2. So this is the AAC coder using spectral band replication and parametric stereo to get acceptable quality at a modest rate of around 10 to 20 kilobits per second, and including some adaptability between speech and music. So they've kind of got to the same point. Okay. All right. So, how are we going? 6 o'clock, so that's just about finished with audio, unless there are any questions.
This graph is about decreasing rates, but the quality is increasing.
The quality is decreasing as well. Well, the rate here, I know I haven't even got a scale, but it's supposed to be showing that the quality and the rate are dropping here. The quality and the rate are increasing here, but we've kind of converged on the same sort of area. So I would suggest we continue at least and talk about the project for a bit, and then we'll have a break. Is that all right? So this short pack I uploaded to the projects part in the LMS, and I just wanted to make sure. I thought it's only fair to talk to you about how I intend to mark the project, what my expectations are, and talk about two important aspects of it. So. First of all, there's that detailed PDF document that talks about what you're expected to be producing in this project report. What will you demonstrate? These are the things that I expect, or that I'll be looking for, so that you need to show that you understand the topic, of course, and obviously go into greater depth than anything that I've presented in lectures. So some of your topics are completely disconnected from lectures on topics that we're not looking at. So, I don't know, things like augmented reality. I'm not sure if I can't remember if anyone's doing a project on that. I think they might be. Yep. But, so it's not relevant to the lectures. But if you're looking at, for instance, the most advanced video coding systems, then it's useless for you to give a report back to me describing what I've described to you. So you would be looking to go beyond what has been done in the lectures, of course. You should be drawing information together from a number of sources, and not just one research paper or one textbook. But while I don't have a minimum number of references, I'm expecting you to not just rely on one source. And where it makes sense, I want you to be concentrating on the leading edge. So what's happening? What's the latest in this technology area? Not, historically how have we arrived where we are, but what is the latest technology in augmented reality? Where do you think it's going next? If you're doing a practical project, and I think there's no one said straight out that they were going to do one, but some people said they might include some degree of some sort of simulations, but clearly you need to experimentally investigate beyond the topics discussed in the lectures. So I think this is a safe example. Don't think anyone's doing it, but suppose, just to illustrate the point, that you were looking at motion estimation techniques, then you would do much more than just compare exhaustive searching with the telescopic searching approach. There are other techniques that I would expect you to investigate and simulate and provide some conclusion about the different trade-offs and so on. And of course, the reporting bit is that you need to demonstrate that you can prepare a highly readable report that's logically developed. And I'm after some sort of a conclusion about the technology area. I don't want you to say this technology is good, this technology is bad, but how is it changing? What alternatives are there? What do you think is happening, and so on. Okay. So where will the marks come from when I'm marking your reports after you submit them after week 10, I think, was it? Week 9 or week 10? This is what I'll be looking for. So 30% of the mark is based on the presentation structure, whether it makes sense. Can I easily find my way through it? There needs to be an executive summary, and we're going to talk about what an executive summary actually is. And the idea of an executive summary is that it's a summary version of the whole report, but not an abstract. It's a very important distinction, but we'll talk about that in a moment. What's the technical depth? Of course, it's a major component. So does the work go beyond what was covered in lectures? Are there any obvious holes in what you've covered? The bottom line is, am I convinced that you've actually learned something, or are you just sort of regurgitating stuff from papers without really understanding it? And some sort of conclusion or recommendation is worth about 10%. And not only do you have a section called conclusion, but do you actually draw some sort of conclusion. And references are important, and they'll constitute 10%. So you're expected to include references, but also are they sensible references that are reliable? You can't just refer to Wikipedia. Is it a peer-reviewed journal, an IEEE paper, or something that you're referring to, or is it someone's blog? And the reference needs to be sufficient that that a reader can easily find it. Right? So just saying Wikipedia is not a reference. You need, if you are, I'm not saying you can't use Wikipedia. It could be one of several references. But it needs to be the specific page on Wikipedia, not just Wikipedia globally. Okay. So that's always the test that I'll apply in looking through the list of references. Can I go there immediately and get it, or would I have to start Googling to try to search to find what you actually meant? Plagiarism, unfortunately, is an issue we need to deal with over the years. I've had to report where I come across examples of plagiarism, and that's a good way to fail, basically. We'll talk more about that in a second as well. Okay, this executive summary thing, it's something I attach a lot of significance to, and it's because it is really important in industry. It certainly has been my experience at Telstra. An awful lot of the time I would be working on or presenting some work from guys who've been working for me to senior management, and there'd be lots of slides in the slide pack to explain exactly all the interesting technical detail, and I'd get to the end and the senior manager would say, "Great stuff, now I want it all on one slide," because he wants to put it together with 8 other things that he needs to present to his senior manager, and so it needs to be really concise. And also, if you're, imagine you finish this master's degree, you go and get a job in some research lab, and you carry out some important investigation over some months. You collect together masses of data, and you write this big long report. It's important that it be there, and it's important that your peers can read it. Go back and check it, and others can check it, but your managers will never read it. Right? So what they want to know is, what's the bottom line? What do I need to do? Right? What decision should I make as a result of what you have said? So an executive summary is a summary of the full report. It's not an abstract, as I said before. It shouldn't say if you, paraphrasing, it shouldn't say, if you read this report, you'll learn this, because I haven't learned anything. I've got to actually get the key outcomes from the executive summary. So it doesn't contain all the detail, it doesn't contain references or diagrams, but it does contain information on which the reader can act, as I say. So it's a bit like, another way of looking at it is you meet your chief executive officer in the lift, and you've got 30 seconds. He or she says, "What are you working on? Why is it important?" So you've got 30 seconds to summarise it before you get out of the lift. What are those key points? You're not going to tell them, "Well, if you read my report, you'll find out about this system," because it hasn't informed them in any way. So an executive summary is not a list of topics that I could find out about if I read the full report. So we're going to have a little exercise to wake you up. I've got 2 examples. These are actually examples from past student reports in this subject. So here's one. I know there's a lot of text. You don't necessarily need to read all of it. This is A and this is B. And apart from the length, I want to know which is a good executive summary, or which is the better executive summary. Just take your time. As I say, you don't need to read all of this text, just get a feel for what's being explained. And the length is not the important feature. Remember that we're summarising, say, a 3,000 word report. So they're both a length that could summarise it. So can I show the other one? Yeah. So okay, so everyone has to vote. Who says this is the better executive summary? Who says this is the better executive summary? Some people aren't voting.
First one.
Sorry?
The first one is better.
First one's better? Why is the first one better?
The information is too much, but the cut it's taking some content and he's stating some statements like we don't need any reference for that.
Yeah, I agree with you. I think this is the better one. It's in fact, I agree that it's maybe got a bit much detail.
Yeah.
I decided to just copy verbatim what was actually presented. So maybe this thing about the block sizes isn't all that important, but look at this paragraph here. Objective comparisons between H.264 and other coding standards such as MP2 blah 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 have shown that H.264 has achieved hit rate reduction of about up to 50%. I've learned something.
Yeah.
Okay, so as the CEO in the lift, hey, I know that I should be thinking about using H.264 encoders, but there is an issue later on. There's this issue about coding complexity. So there's information. It's not complete. It doesn't have all the detail. I contrast it with this one, where this paragraph is describing the sort of thing that I said I didn't want. Right? If I read that paragraph, that second paragraph, admittedly the first paragraph does tell me something about DVBH, but this second paragraph says, if you read the report, right, I've got a summary of the system, there's an overview about the physical layer and link layer, and next the functionality of IP datacast is introduced. Nothing here, it's all introduced in the report. And then after, right, there is a conclusion. I don't know anything that's in the conclusion, but there is a conclusion. Okay? Is everyone happy that they understand the difference between the two? That's good because you've got another test. There's another two. Right? So, yes. So here's A and there's B to follow on the session. You're a very fast reader. Okay, there's the second one. You guys are impressive. so who's voting for this one, the first one? Fast learners, eh? So this commits the same sin, right? Same crime. It says it's listing all this stuff that I can read about if I read the actual report, but I don't learn anything from this. Think of your... Okay, there are some technical terms being mentioned here. The features of the DVBH time slicing, forward error correction, multi-protocol encapsulated data, 4K mode. Now, if I'm a CEO, I have no idea what they mean, right? And there's nothing that will help me understand it from here. So, after explaining all the four standards, comparison is made, but it's not summarised here. Okay, whereas in the second one, again, it's not necessarily an ideal executive summary, but I'm learning stuff, right? It takes as much as 3 times longer to encode the same movie by the H.264 encoder than by one of the other ones. I'm getting some summary information that I can actually use. All right. Okay, good. It's really is a very important to be able to summarise your work. Okay? To be able to explain it to someone, and to be able to provide a written summary, which is why I attach as much significance to this executive summary. So the other thing we need to talk about is the plagiarism thing. You're gathering lots of information from different sources and putting it in your report. The definition of plagiarism is there. There's a reference to the university's treatment of plagiarism. So plagiarism can sometimes be accidental or it can be intended, but it's effectively representing someone else's work as your own, whether you mean to or not. And I've got some examples to show you to see if you think this is plagiarism or not. So this is a report that someone submitted in this project a number of years ago, and in writing this report, they've provided this paragraph about IP. Can't remember what the actual report was about. Doesn't matter. Anyway, so there's this paragraph here which has a reference 10, so we know that they went here and they got some information from there. But if you go to reference 10, you'll see that that text is repeated, or appears verbatim up there. So, but they have provided the reference from which they obtained it. So, is that plagiarism? Anyone not think it's plagiarism? It is indeed plagiarism because there's no input from this student in combining or understanding the multiple sources of information and then synthesizing their own description of it. All they've done, even if maybe their thinking was, I can't think of a better way to describe it than this, I'll just copy this and use it. What they've effectively done is just taken that, copied it, put it there, and presented it as if they have written it themselves. So that is indeed plagiarism. So here's another example to think about. So here we have there's no reference to the source, but in fact I found this just because it didn't the English didn't sound like the student's English, so it's easy. You just take a sentence and Google it and you find the source. So within that report there's this bit, and so they're not copying whole paragraphs, they're selectively taking sentences here and there, or parts of sentences here and there, and using them. So, is that plagiarism?
Yes.
Anyone not think it's plagiarism? What a very intelligent group you are. I'm sure I won't have any problem.
What about definition from ITU?
Pardon?
What about if they define something in ITU and you want to use their definition?
Oh yeah, that's fine. You can take anything and put it as a quote, right? Right. Just make sure it's clear that it does come from some other source. That's fine. Yeah. I mean, you wouldn't want to put too much of that in your report because you're not adding that much value. But if it's a particularly valuable quote, then just present it as such. Just put it in quotes and say, from, and this is the reference. So, in summary, I know I'm possibly flogging this message, but your work needs to be literally your work. You need to demonstrate that you're the one who finds the relevant sources, understands and interprets them, can analyse and extract information and synthesise your summary of them, answering the questions that you've asked yourself. You know, if I'm doing a study on augmented reality, I've decided these are the questions I'm asking myself. This is what I want to answer. Let's read this reference and this reference and this reference. Here I've got a little bit of information from each of them, and when I put it together, this is how I would summarise it. And when you're doing that, it's literally a good idea to read the reference and then close it. And so you don't even see the words in front of you. You just think, well, okay, right now, what do I want to say? Why am I making such a big point of it? Well, it's a waste of time, me putting time in trying to convey this information to you if you just throw it away by failing the subject because of this. Because if I discover the plagiarism, then I'm obliged to report it to the head of the department. You end up having a discussion with them, trying to justify it, and most likely you'll fail the subject. So that's a waste of everyone's effort, and it's time consuming for me. I'd much rather spend the time reading an interesting report rather than trying to get evidence of the plagiarism. Interestingly, not that I think you would do this, but just it's an interesting kind of development of time. That last year there was someone who well, in fact, an academic at another university contacted me because they had a student whose report was very similar to one that my student had submitted. And so at first I thought, well, that's impossible. Right? How come it hasn't been published? So how did they talk to one another? It was in another state. And what had happened was that they were both people for whom English was not their first language. So they had both gone to the same reference in another language and used Google Translate and both copied it into the different reports. So even that can be found these days. So it's actually surprisingly easy to detect. Anyway, enough of that. It's 6:30, so why don't we have a short break for 5 minutes or so, and then we'll start this new topic. Unless there are any questions about the report. Yeah.
Is there any tools can help us to check the errors and stuff? Because sometimes we are probably not mean to do that, but because we got long reports, so probably we miss something in the report. So is there any tool we can like upload our document and we can check for that?
Well, actually no. Because, and the reason I say that is because there is Turnitin. You're familiar with Turnitin? Yeah. So that's the analysis tool that will look at your report when you submit it. And once a year or two ago, students asked exactly this, and I thought, well, that's not unreasonable. Let's allow two uploads. But what happened was that they uploaded, and then they saw wherever there was a match, just a random match, just because the words that you had chosen just happened to match a phrase in a report somewhere or something else that someone else had submitted. And so the students started changing it to try to avoid any match anywhere, and it destroyed the report. It was unreadable. And a small amount of matching just by chance is not a problem. When I get the Turnitin report, it'll show probably if you show 5% or 10% of matching with some other things, and it'll show the little random phrases, and I'll just ignore it. I won't even look at it.
In our department, we don't want to maybe put ourselves into risk, so
Yeah,
we
yeah,
want
but-
some
but-
tools to help us.
Yeah,
It's not
yeah.
convenient.
No, well, but if you're writing it, then it won't. There will not be a great paragraph that will align will match with some other document. So, unless there's a significant match of a large block of text, I don't even look at that.
5 to 10% of matching is good.
Yeah, it shouldn't be an objective, but that's right. Okay.
So we have
No. I would like to include it, but I just haven't got time. Okay, so 5-minute break, have a drink, we'll walk around.
Please do not send me email about my project is about the machine interpolation. I think you might remember. I sent you an email.
Yep.
And
Oh, yeah.
I think it will be a practical
Good.
project. And
Okay.
what I think is I will use some time to. What I want to do is to start with 2 frames and try to generate the frame in
Intermediate.
yes. So I will use some time to figure out algorithm or something based on MATLAB to do these things. And I think if it okay, if I can't do that, maybe I will to refer to some other algorithm
Right.
and do some improvement or things like that to make it better. Is it okay?
Yeah, that sounds good. Well, I mean, you'll do your simulation based on some reading of what what techniques there are, rather than just
And
pick it
see
up.
if it's okay, and I will do some of them
Yeah, but
improvement.
you wouldn't start just thinking up how you
Yeah.
might do it. I mean, you'd be better off doing some reading about
Yes, yes.
techniques that exist
Yeah.
already, right? And then, given that background, then you would implement something and see how it works.
And what I can think is the start with the motion vector, and because the motion vector is this block moving to the network
Yeah.
between the frames,
Yep.
so we can find the middle one
Yes.
by using this.
Yes.
That is what I think now.
Yes.
So I will
And
do
then
that.
think about.
So what I need to do is try to find the motion vector by using the MATLAB and also maybe some others algorithm to find the motion vector first
Yeah.
and then doing the other thing next. So
Yep.
is that okay?
Yeah, that's okay. But there are two things. One is that remember that the motion vector gives you the best prediction. It might not necessarily be the motion. So, does that make sense? It might not. The best. What gives you the smallest prediction error might not correspond exactly with the motion of the object, right? Because there might be another part of that block that actually matches better, even though it's not the same direction as the motion. So that's just something to be aware of. And then, of course, the other thing is that there might be for your intermediate frame, there could be some pixels that are missing.
Yes,
So you
yeah.
need to interpolate them somehow.
Yes.
Yeah.
Yeah.
So yeah, have a look in the literature to see how people have attacked that problem, and that might save you time for when you do yours. Yeah.
Okay.
That sounds good.
Okay, thank you.
Yeah. So let's start again with this one. Okay. Lapel microphone is dead, so I shall try to stay near the bench for those relying on the recording. Okay, so the logic, as I mentioned earlier, is that now that we know something about the multimedia formats of data that we are carrying and how they are constructed and some of their sensitivities, let's now start to think about how we can transport some of them. So I want to talk in this segment about some fairly generic sort of technology components about multimedia transport, but later in the lecture series I'll look at some specific case studies. So we'll look at streaming media, multimedia over the internet, for instance, in more detail. We'll look at digital TV in more detail. We'll look at digital cinema in more detail, and maybe multimedia over mobiles or something, I'm not sure. But to consider some of the generic issues that concern multimedia transport, one of them is timing, the issue of managing buffers and the timing requirements of our media, and also how our media will behave in the event that there are losses or errors, because this can obviously occur with transport. So if we go way back to topic 1, we were talking about what's so special about multimedia content, by looking at compression and the formats of multimedia, we've covered those issues of the fact that multimedia content involves large bit rates and file sizes, and also the quality requirements, which depend on different applications. So what we want to look at now is some of these transport related issues, the fact that we need to combine those media types. We have multiple media types, we need to have timing requirements, so we need to synchronize them, multiple media, and we have continuous playout requirements in the case of video and audio, and also we have some error tolerance, because at least in the case of distributing for human receivers, we are tolerant of the occasional error in continuously played out audio and video, where we would not be tolerant of such errors in the case of a data application or a Word document or a PDF or something like that. Okay, so we've got those boxes up the top there. We've looked at audio encoding and decoding and video encoding and decoding, and I think we discussed briefly in the first lecture that there may be other media types such as subtitles and metadata. But to carry all of this combined data over some communications network, there's something missing in the middle there. And what's missing is commonly referred to as media containers. So these are the structures that put together the video with associated audio, for instance, look after timing with these clock reference signals and so on, and combine the media together in some way, providing multiplexing, synchronization and timing before the data is then carried over whatever transport mechanism is relevant. So this media container layer is sometimes called a wrapper, combines the media components and manages timing and synchronization. So we need to be able to identify the media components. So at the receiver, it's no point just receiving a bit stream that's been pulled out of this multiplex. We need to know that it's an audio bit stream, and we need to know that it's encoded using AAC, and we need to know the relevant parameters of that. There are many applications where we need to know the association between the media, so we need to know which video and audio tracks belong with one another in a TV broadcast, for example, to make sure that we can play them out correctly. And we need to know the format of the media so it's played out using the correct decoder. It goes to the AAC decoder and not the MP3 decoder, for instance. And there's the synchronization issue that I already mentioned. So that's what we'll be touching on some of those, as I say, the generic issues in this topic. The first one I want to look at is buffer management. We've talked a little bit about buffers. Right? Remember the variable rate, constant rate thing, and this feedback loop and how we manage buffer fullness. But I think we did talk about this earlier, but there must be a corresponding buffer at the input to the decoder, because at least think in this case of constant rate transmission networks, we're filling this buffer at a constant rate. We're reading data out at a variable rate, and so that buffer is essential to provide the interface between the two. So why is that variable rate? Why are we reading data out of this buffer at a variable rate?
Well, that's the data rate. So how you do that if some, like let's say some images that doesn't require high quality, so we send low less bits, and if images that require high quality or high definition, then we send more bits.
Yep.
So that's why variable.
Yeah, well, the key point is that after that encoder there we have a variable rate. So we've got a variable rate describing each frame. And so if we generate a variable rate or say a high data rate for frame n, then when we read the data to describe frame n and generate the decoded picture for display, then we need to read out a large amount of data in that frame time. Then the next frame might require a small amount of data. So a smaller amount of data will have gone from here into that buffer, and we'll be reading out a small amount of data from the buffer out to here. So if we've got this constant rate link between these encoders and decoders, and we don't always, right? We talked about where we can actually transmit a variable data rate. But in the case where we've got a constant rate, we certainly need these buffers as interfaces between the two. So this is we talked about this, I think, this mirrored operation of buffers, did we? No. Okay, sorry. So this is just reiterating what we just talked about. So if at a particular time in the video we generate a large amount of data, then this buffer will fill up. But at the corresponding time in the decoder, so the corresponding frame, not the corresponding full clock time, the corresponding frame, then this decoder will need to read out a large amount of data, so that one will go down. So these buffers will end up mirroring one another. For frame n, this one will be, if this one is near full, that one will be near empty, and vice versa. They will go up and down in opposite ways. But we need to make sure that both of those buffers never overflow or never underflow, because then of course we've lost data, or we're trying to decode data that's being pulled out of an empty buffer. So we've got we'll be just showing a buffering message. We can try to, if we have to part load these buffers before we decode, then that implies that there's going to be a delay of some sort, right? Because we need to partly fill this buffer before we can start reading out of it. It goes across the network, then we've got to partly fill this one before we can start reading out of it over on this side. And we need to manage those buffer levels in some way to make sure that that they won't overflow and underflow. Okay, so the encoder here can manage this one. We've got this feedback mechanism, But what happens at the decoder? It's really up to the encoder to tell the decoder what to do about this buffer if it's going to make sure that that it's not going to overflow. In terms of this delay, this inherent delay in part loading these buffers, there are ways to try to reduce that. For instance, if the network is fast enough, if the network has sufficient capacity, then we could dump faster than real time a little bit of this data here, right, to preload that buffer before the decoder starts reading out, so we can dump that data as fast as the network will allow us to. So Windows Media Services has this fast streaming playback that does this, for instance. Okay. So let's just look at an example of that mirrored operation of the data buffers. So this is the example of the coding of Jurassic Park that we looked at for another purpose before. And you'll see that it's got this variable data rate, so this is the number of bytes to describe each frame as we go over these hundreds of frames. And so we can look at the behavior of these buffers, because this plot here, or the data that it represents, tells us for each frame how many bytes go into the sending buffer, and at the corresponding time how many bytes are emptied out of that buffer, okay, to describe the frame in both cases. So we describe frame 652 with about 700 bytes of data. That's how much goes into here at frame 652, and at frame 652 here, then we've got to take out what did I say, 700 bytes of data. So then, just to get a model for what's going on, we can assume a constant transfer rate between the two, and decide how full this is initially before we start emptying this buffer, and decide how full this one is before we start decoding it. And so if I've taken that data and done exactly this with just an Excel simulation, and what I've plotted here is what the sender buffer will look like and what the receiver buffer will look like at the same picture number. So again, this is not the same wall clock time, because what happens at the receiver is somewhat after what happens at the sender, but for the same picture number, you can see that they're exact mirrors of one another, as we discussed before. So we're over this period of time, we're generating more than the average number of bytes per frame. The average number is the rate at which we're transferring between the two. So if we're generating more than that average over this period of time, then the sender buffer will start to fill, will continue to fill. And over this period of time, and at the corresponding period in the decoder, in the receiver, then we're using up data faster than the average at which it's being filled, and so it will continue to start to be emptied until we get to this point where the picture characteristics change, and the reverse is true, but they remain as mirror images of one another. What this is showing, though, is that my simulation parameters were not very good, because I've allowed each of these buffers to empty at some point, so I need to actually preload them with even more data, which introduces a bit more delay, to make sure that that doesn't happen. But to do that little simulation, just to put some numbers around it, we preloaded the receiver buffer with 240,000 bytes. The transfer rate was chosen at 4,000 bytes per frame, only because that's about the average at which the data is generated over the long term. So with that constant rate in between the buffers, I set an initial sender buffer level of 70,000 bytes. so that's here, and that turned out to be not enough because over that first period the buffer emptied, so I should have started it a little bit more. I set an initial receiver buffer level of 240,000 bytes, so I had to wait for what's that, 60 frames of data, 4,000 bytes per frame, so 60 frames of data before I started decoding here. So when we look at that amount of data having to be transferred at a total of 310 kilobytes, transferred at 4,000 bytes per frame, or 4 kilobytes per frame, that's 77.5 frames, and so that's about 3 seconds, just to get a feel. Does the calculation make sense, where that's come from? Yes and no? No? Okay, so just to get these plots up into the positive sector, and they're not quite there yet actually, but just imagine that they were all up in the positive sector, so no buffer emptied or so no buffer underflowed during the simulation. Then we need to which is the best? Yeah. We need to part load this this buffer, so we need to be generating bytes and loading into this buffer to a certain level before we start reading out. Right? Otherwise, we'll start reading out too soon, and we will empty the buffer some short number of frames or seconds afterwards. So, if we have to put in, say, I think the number was 70 kilobytes, then if we're generating data at an average rate, it is a variable bit rate, but if we're generating data at an average rate of 4,000 bytes per frame, then we can calculate how much delay after we've started our video will go into just preloading that buffer before we send anything. Okay, and at the other end, a similar thing happens. If we have to preload this buffer with, I think it was 240,000 bytes in my simulation there, before we can start reading out and decoding it, then again that's a significant delay just to preload the buffer before we can start reading material out. Okay, and so so that's where those numbers came from. The 70,000 bytes initial sender buffer was to move this plot up to try to keep it in the positive area, although it didn't quite make it, it's close. And the 240,000 bytes was the initial fullness of the receiver buffer before it started decoding, because it was found that it was using up so much data each frame on average here that the buffer was eventually going to empty unless we started with a large initial fullness. Okay. So there are some limitations of what we've just done there. Ordinarily, if we're encoding at a variable rate, it would be because we can send and store at a variable rate. There's a very wide range of number of bits per frame in that particular simulation because it was for a variable rate transmission. So that's why we had quite long delays. And also, if we were generating very high rates at some particular time, then we would ordinarily have some sort of a feedback to limit that. Normally for constant bitrate coding, so that was what the simulation was for. Maybe I'm confusing this a little bit, but this simulation is trying to show what happens when we have this constant transfer rate, even though a variable rate was generated. But that was actually, that simulation was for a truly variable rate, not just one that was variable over a short period and then controlled with a buffer feedback, but one that was allowed to continue as a variable rate. So there are other traces that we could investigate. Here's a encoder operating with that feedback loop and generating a target bit rate of 256 kilobits per second. So if that average of 256 kilobits per second varies over some short time interval, then that feedback mechanism will go into place and increase or decrease quantizers, which increases or decreases bit rate accordingly. So there isn't quite so much variation in that case. Anyway, in the end, the message is that we need to control those that buffer fullness, and while we might have that feedback mechanism at the encoder where everything's in our control, we don't have that control at the decoder. So what do? Well, the solution is that the encoder needs to tell the decoder something about buffer fullness. So the solution that is adopted within MPEG, which is pretty similar to others, but we just use the MPEG terminology, is that there's a virtual receiver model that's that is calculated at the sender, and this virtual receiver is called a video buffer verifier, and in the end it turns out to be quite simple in terms of the parameters that are sent to be able to control what happens at the decoding end. So we simply tell from the encoder to the decoder, we tell it the VBV buffer size. So this is saying that the encoder tells the decoder, I assume you have at least this number of megabytes of buffer available. Okay? And the second parameter is this VBV delay, which is saying you should wait this amount of time before you start decoding and displaying. Okay, so it allows, that's the way that we can pre-load the decoder buffer before we start reading out and displaying, decoding and rendering. Maybe this next diagram will make more sense of that though. So this is a simple sort of MPEG 1 or MPEG 2 style encoding. And so the encoder has said to the decoder, I assume you have at least VBV buffer size bytes available to me. Because if that's less than, say, if it was less, I'm assuming I'm about to tell you to fill your buffer to a certain level, and if we haven't got that number of bytes available in the buffer, then I'm going to overflow it. Okay. So that's the first parameter that the encoder sends to the decoder. And the second and last parameter it needs to tell it is what this VBV delay is. So if we are transmitting at a constant bit rate, for instance, the decoder starts to receive data at this time, and it waits for this amount of time, this VBV delay, and only at that point is it allowed to read out and start decoding and displaying video frames. Yeah. And so from that point on, the encoder has a model of what's going on here. And so it will manage the amount of data that it sends, that it'll be another parameter that restricts how many bits are generated for each of its frames, because it has this model of what's happening in the decoder and needs to make sure that the decoder buffer doesn't overflow or underflow either. So let's just go through this illustration in a little bit more detail. Let's see what's happening. So over this time that this VBV delay period is occurring, so the decoder buffer is filling but nothing is being read out and displayed, then data for this first I picture and this first P picture and B picture are flowing into the decoder buffer, but they're not being read out yet. Only at this instant can the decoder say, okay, give me the first frame. It's an iframe, so it has to read out a lot of data. This shows how the model is a little bit simplified. The VBV model assumes that all the data for a particular frame is read out instantaneously. So it might be a bit unrealistic, but we need some sort of a model, and so that's the way it's applied. That's a worst case. So at this instant, the eye picture data is read out. Right? The eye picture data might have been written in over, I don't know, over sort of this period. Then we would have gone on to start putting this data in, but it's actually only read out at that instant. And of course, the buffer fullness drops significantly because the eye picture requires a lot of data. And then, for all periods of time, we continue to fill the decoder buffer at a constant rate. That slope is always the same, but at regular frame intervals we read out the varying amount of data that describes each frame. Yeah. Of course, the display order is different to the transmission order. We talked about that because of the B frame thing. So this P picture is decoded, is read out of the buffer and decoded, but it stays in the decoder used for prediction for these guys before it's actually displayed. But that's getting back into the video coding side of things. Does that make sense? That diagram makes sense? Right, so I've been trying to get to the point where I can explain that we just need those two parameters, and for the encoder to model what's happening at the decoder, and we can make sure that the decoder buffer doesn't overflow. Right, so let's talk about a little bit about clocks, because from possibly before you started looking at this subject a few weeks ago, you might have considered the communication of continuous media like audio and video as being one in which just all the clocks are locked. It would be fairly straightforward. We've got this frame rate f, that would, if we had x bits per frame to represent each frame, then f times x would give us y bits per second, and then that would be converted to some sort of symbol rate. And at the receiving end, we would have a certain number of symbols per second, and we would that would give us a certain number of bits per second, and that would give us a frame rate again. So everything would be locked in synchronism. However, the situation, particularly these days, so these digital days, is a bit more complicated. So we have audio and video, at least. So there are at least two different clocks, right? Could we derive the audio sampling rate from the video clock? Well, probably, but we have at least audio and video. But we might have multiple independent sources transmitted in the one channel. So with our television broadcasts, for instance, there's one multiplex that's carried over one carrier that includes maybe 3 or 4 TV channels with different, from different sources that could have different frame rates. I mean, they're all 25 hertz, but one might be 25.001 hertz and one might be 24.998 hertz, and so on. This is not true, of course, right? We now know that we generate a varying number of bits per frame, so there isn't this direct connection between bits per second and bits per frame. This network connection in the middle could involve a certain carrier frequency of known frequency and relationship to the clocks, but it could also be a packet switch network like an IP network in which we've essentially lost the clock in the middle. And these days the situation can be much more complex. We can even do things like receive part of our media, our multimedia, by broadcast TV, and some other part via the internet, and then we render them together on a tablet, and all sorts of possibilities there. So this is an overly simplistic picture, although that's what life used to be in analog days. It's interesting to note that when there was an outside broadcast, say from a sports stadium, if this camera was in a sports stadium, then the entire television broadcast station would end up locking itself to the frame rate that came from that particular camera, right? So, then when it switched over to another camera, it would have to lock onto that camera. But as I said, the digital environment is very different. So we need to recognise that we don't have a common clock throughout. So as a result, this frame rate here could drift from that frame rate there. Okay. So we need to be aware of that. And we also need to be able to define somehow when we are going to play or display certain elements. When do we, at what instant do we play out a particular frame of video or a particular sample of audio? So the answer is that we are told by the encoder when to do it. We actually use timestamps. So all the encoders do that. But a measure of time has to, we need to know what the actual time is. If we're going to say, have a timestamp that says this particular piece of audio needs to be played out at this particular time, this instant of time, then we need to be able to measure that time, and we need to make sure that that time remains in synchronism. So to fill in the gaps in here, we have different timestamps. These are MPEG, this is MPEG terminology for the different timestamps. We'll look at an example in just a second. How do we know what the time is? Well, we could look for a common reference. In the internet world, there's this NTP, Network Time Protocol, which attempts to allow different devices to synchronize, but really it's more a matter of getting the same. It's only accurate to sort of 100 milliseconds or so. It's to allow us to automatically get the actual wall clock time for our laptops and our tablets and so on. So it's not going to be it's not going to give us the accuracy that we need to be able to say that this piece of audio needs to be synchronized to within, so some 10 milliseconds, say, of a piece of audio. So the alternative would be to get a clock reference signal from the encoder. So a program clock reference or something similar. We'll talk about that as well. How do we remain in time synchronism? Well, if we could use this NTP thing, we could keep on referring to it, but as I've said, that's not really going to work. Having synchronized a local oscillator, could we just run it, let it run freely? Modern crystal oscillators are quite stable. Anyway, if what would be the consequence of the clock at encoder and decoder drifting away apart over some long period of time, or maybe there'll eventually be a glitch and we'll lose a frame or something like that. So it's, I just think we should take a moment to consider whether we really do need to keep these oscillators in synchronism, or do we keep monitoring these time reference signals? And how do we handle that in the case of something like a packet network where we could have jitter? Yeah? So we might send off a clock reference signal at a regular interval from our encoder, but because of jitter they arrive at different times at the decoder. So that's what we're going to explore over the next little while. First of all, the timestamps. So the timestamps are instructions to the decoder to tell it when to display an item. So the idea is that each little packet of audio or video data, let's stick with the media examples, includes a timestamp, and the timestamp says that this piece of audio, or the start of the first byte described by this piece of audio, needs to be played out at time t1, and or this picture needs to be played out at time t2, and so on. That's fine. That's a great way to synchronize our audio and video, and to make sure all of our events are in sync, provided we know what the right time is, of course. And it doesn't matter whether we have a continuous data stream, such as a TV broadcast, or if these are packets of media in IP TV, for instance, Netflix. The same thing applies. We can still insert these little time references, these timestamps, to say this is the time at which this should be played out.
Time T1 within T2, inside T2. As the audio edit.
Yeah.
Let's say the video one is like 2 minutes. Let's say it's
Right.
like the computer gonna save it,
Oh.
right?
So this is not a time interval. It's the time. It's saying that if we're counting, let's say we're all counting clock pulses from a particular reference point, then actually I've got an example of a clock, a timestamp in the next slide. But it's saying at this particular pulse number, that's when you should be playing this audio, and that's when this video, this frame should appear. Just if you hold on to it for the next slide, maybe it'll make more sense. So here's an MPEG example. MPEG uses a 90 kilohertz clock. It's just convenient to be able to divide down to get the different reference rates that we need. And there are actually two types of timestamp that are used. One is a decode timestamp. So that's the time at which you should decode that particular frame of data. And the presentation timestamp, which is the time at which it should be actually displayed. Right. So just as we're going along, think about why we need both of those. So these are just counts of this 90 kilohertz clock, assuming that encoder and decoder both have these clocks available. We'll talk about how to synchronize them in a moment. So for this particular frame, we have this count for the decode timestamp, and the presentation timestamp is the same. So we should decode at that instant and display at that instant. Same thing here, and I think we can look at the differences just to make sense of the numbers. So you'll see that the increment between these counts for each frame is 3,600, and if we divide 3,600 by 90,000, then we get 0.04, 40 millisecond frame time. Okay, so that's the number of clock pulses between frame counts. Okay. Here we've got a difference between the decode timestamp and the presentation timestamp. Why do you think that might be the case?
So at that time maybe buffer is that time that encoder has told the decoder that until this time you should full your buffer. I mean, until that time you should not present that.
Yeah, but why wouldn't it present it? It's told to decode it at this time, but hold on to it and present it only because it's a P frame. That's right. Yeah. So this P. Yeah. So we decode this P frame, and we keep it available so that we can decode this one and display it. So that we decode this one and display it, but this one won't be presented until after. Hopefully the numbers make sense. After this one, right? So that's the thing about transmitting it in one order and displaying in the other because of the B frames, because of the existence of the B frames. Yeah? Okay.
case is exactly the same because it will take some time to decode that and then present it.
Yes, that's a good question.
There has to be some milliseconds delay.
Yes, you're right. You're right. I'm not sure of the mechanism, but it's a good observation. Yeah. Okay, so this is how, apart from your question, I'll have to think about that. So this is how our timestamps work, and we have similar timestamps for similar timestamps for the audio. And if we have timestamps to the audio, then we can tell very precisely when the decoder should be playing out the audio to make sure it synchronizes with the file. Sometimes these things don't work, as you've, or they haven't been configured properly, as you've probably seen from various clips on the internet and stuff, but they should work. There is the mechanism to provide that they work. So the timestamps are only useful if the encoder and decoder keep the same time, right? Because if they're not, then buffer levels are going to gradually empty, and we'll have underflow or overflow, even though the our buffer management communication should keep everything in sync. So even if we had just a piece of wire connecting the encoder and decoder, it doesn't have to be a packet switch network. Even just a wire connecting encoder and decoder, we still need to make sure that we manage those, that we understand what our buffers are doing, that they won't empty, they won't overflow, because our clocks are different. So what happens if we lose relative timing between the sender and receiver? So if our encoded media is being sent via the web or via some other network, or even stored on a disk, right, where there's some disconnect between the clocks that are used at both ends, right? So this is generating a 90 kilohertz clock, and this is generating a 90 kilohertz clock, and this is sending timestamps to say, according to your clock, this is the time instant at which you should display this B frame. But how do we make sure that these clocks are the same? Is the question that we're now going to discuss. So inside the receiver, what have we got? We know we've got some sort of a buffer there. We're receiving information and we're putting in this buffer, and the local clock is deciding how fast we read, or the instance at which we read information out of this buffer. The buffer, I keep on saying this, the buffer can't be allowed to overflow or underflow. So we've got these, this VBV thing is managing it, but it assumes that the same clock is at the sender and the receiver. So I mentioned that we should just consider how important this is, right? Because we do have crystal oscillators that are reasonably stable. So here are a few numbers. So typical crystal oscillators, according to my information, should be within about 1 part in a million of one another. So let's just put some numbers here. Suppose this actually comes from an ITU-T document that discusses this issue of clock synchronization. So suppose the nominal clocks at the A to D and the D to A clock, this is for speech, of course, 8,000 hertz. Suppose the source clock is actually a little bit under that and the destination clock is a little bit over that. Then there'll be this number of extra clock cycles per second at the destination compared with the source. Eventually the de-jitter buffer will empty due to that offset. So if the source clock was exactly the same as this, then everything would be okay. But because this one's getting a little bit behind, if we're not generating samples quite as fast as we're trying to decode and play them out, And the drift between the two clocks is that amount. So if we assume that the de-jitter buffer is sized to 20 milliseconds, maybe something of that order, then we can calculate how long it would take to for that clock asynchronism to empty the entire buffer. So the encoder assumes the buffer's full, but in fact it's been emptied, and it actually is quite a long time, so more than, that's 11 hours. But if you take the extreme cases of 1 in 10 to the 6, then this can occur in around an hour and a half. So it's for short connections, maybe it doesn't matter. So for a VoIP connection, so if you were trying to, if you had clocks in your VoIP phones like this one, and they were running on as a free oscillator, then maybe you wouldn't worry about trying to synchronize them. But for longer communication, it's at the sort of the numbers indicate that it's probably worthwhile. So how do we actually recover the clock? One way that we might think of doing it is just looking at buffer fullness, right? If we're, even though our network might have jitter in it, on average we should be filling this buffer at a more or less constant rate if it's a constant rate transmission system. So could we perhaps look at that buffer fullness of our de-jitter buffer here, and low pass filter that and use that to control the clock. Right? That could make sense, but while it'll control the rate, it won't tell us actually what the time is. We need to somehow initiate it. But also it's not going to work with VBR. Right? If we talked about how that the use of VBR will mean that the buffer may significantly increase or decrease in fullness. And so the alternative that's used is to actually send these clock reference signals that I referred to before. So every now and again one of these packets of data will include a clock reference signal, and even though there's a bit of jitter in the network, we try to smooth that out with a low pass filter function here, and compare the clock reference signal that we get with what the local clock is, and make some adjustment in this sort of arrangement. Right? So we have we've got a voltage controlled oscillator. It's described in analog terms, but it's it's digital. But we've got a variable rate oscillator here that we count the pulses of that we count those clock pulses, and we compare with the clock reference signal that comes in here. Let's assume that that this is roughly the same as this, but there could be some small difference here. So we take that difference and that goes through a low-pass filter. The low-pass filter is there because these clock reference signals may arrive at slightly varying times because of jitter on the network. But if there's a sustained error between this one and this one, then the output pulse rate from the system clock will adjust accordingly. Right? So if this one is continuously behind this one, then the generated frequency of the system clock will slowly drop to compensate. The question is how we initialize these things in the first place, and the solution that's adopted is perhaps the easiest and most obvious thing to do, and that is when you first start up this system, you first receive the first clock reference you receive is just used to load this counter. Okay? So it might not be super accurate, but it's going to be pretty close. And then after that after you've loaded this counter with the first clock reference, then you monitor all the subsequent ones and see if there's any sustained error one way or the other, and adjust the local oscillator to to suit. So now we have this this combination of our we're sending our media over our network somehow. When I say somehow, whatever the network is, but included there are these timestamps that say where to, what instant the audio and video should be played out. But also every now and again we have these clock reference signals, which is essentially saying synchronized watches. The time right now at the encoder is this. Okay. And the terminology is that the timestamps are the ones that tell the decoder when to render and display, and the clock reference is the one that tells it what the time is. So, question: Do we need the clock to be synchronized in a DVD player? Do you think? Maybe. Why do you say that?
Because the data is saved as a CD, so it's good. Like, you don't need the exact time to be on the DVD, because all that time are stored in the packet on the CD for the audio and video.
Yeah. But the question is, whether do we need to? Okay, we're getting timestamps of the audio and video data that's on the disk, but they are referring to a clock, and they were actually referring to the clock at the encoder at the time it was encoded. So, do we need to somehow synchronize the clock internal to the DVD?
The decoder.
Yeah, in the decoder. Yes. Why? You don't think so?
Yes, like encoder and decoder, they should have the same time.
Well, what's going to be the consequence if the clock is not exactly the same? Is that
There won't be synchronization of the video and so on.
no, but if it's 1 part in 10 to the 6th, then I'm not going to notice that the video is playing out too fast or too slow. But are we going to have buffers that will overflow or underflow? No, I don't think we will, because if you think about what's happening here, we have a system clock, one system clock that's driving this DVD player. It's defining the frame rate at which the decoder is going to be reading data and displaying it, but it's also the one that defines how fast we're reading data off the disk. Right, so if this decoder is saying I've just finished taking that amount of data to define that last frame, I need some more data, then this same system clock is saying, okay, I'll read another frame of data to you. So it's going to control its own buffers, and even if this was substantially slower or faster than the original encoding clock, it's not going to cause a problem for buffers, I don't think.
And then how audio and video will be synchronized?
Pardon, sorry?
Then how audio and video will be synchronized?
Well, they'll still have timestamps,
Yeah.
right? But then the timestamps will refer to this system clock. So the relative difference between video frames and audio data will be as defined from the encoder. Okay. So let's talk a little bit about errors. Bit of a change of topic. If we're sending data over a network, then we need to think about what happens in the event that we have bit errors, or we have lost packets, or what happens. So let's talk at first. Let's consider our tolerance to errors, and then we'll talk a little bit about the effect of these errors and then how we can protect against them. I'm not sure how far we'll get tonight. I'll try to finish by 8 again. So I think this, not sure if I used exactly this slide before, but we've said multiple times that if we're talking about distribution of video and audio for consumption by a human recipient, then we don't actually need it to be 100% accurate. That's not the only scenario, of course, right? We could have machine interpretation of video or automated tracking systems and all sorts of things, automated surveillance systems, but this is obviously a very important and large application area where we are distributing audio and video for human consumption. So if 100% accuracy is not required, what is good enough? What error rate is tolerable? And this is a very hard question to answer because it depends on many things. Ask yourself, how often would you tolerate clicks in an audio stream or odd coloured blocks in a picture? How quickly would you want to see them overwritten? So if there's a funny green block on a picture because there's been a bit error, how fast does it need to be overwritten for the service to be acceptable, whatever acceptable means? So, and it depends on many factors. So it depends on what's the application. Is it my expectations that I've bought a great new high definition TV set, so and I've subscribed to Netflix and I'm paying them money every month, so I expect good quality, or am I looking at YouTube clips and it's costing me nothing and I have low expectations anyway? It depends on what are the temporal statistics of the error or the loss. Do they all occur in bunches or do they occur completely randomly? And also what resilience strategies are used in the decoder to try to hide it. We'll talk about these probably not tonight, but next time we're together, not next week. But to a first approximation, if we don't do anything to protect against errors, then every single error will correspond to a visible disturbance or an audible click or something similar. It might be, depending on which information is actually affected by the error, it might be that it goes unnoticed, but as I say, to a first approximation, you'd say every error corresponds to something that you will detect. And so there have been various attempts to standardize and provide guidelines about what sort of error rate or loss rate is tolerable. So the DSL forum, for instance, says that the target should be 1 error event per 60 minutes for standard definition TV, and 1 error event every 4 hours for high definition TV. And an error event is defined as you see there, so loss or corruption of a small number of IP packets, whatever a small number is. So there's some interesting conclusions drawn here as well. If we look at these numbers, the bit rate for high definition TV is going to be higher than standard definition TV, right? So even though this bit rate is going to be higher than this one, we're actually our expectations are that the error events will be even less likely. Right? So think of if there's the same probability of a bit error, right, 1 in 10 to the 9 or something, then there are going to be more of them per unit time of high definition than there are for standard definition, and yet the expectations are that the delay will be even longer. So I sort of hinted at this before, that the particular information that gets affected by the error or the loss will make a difference in terms of its visibility. And so I have a video simulation that shows this. can just figure out how to get to what I want. Ah. Okay. And not that. Okay. And just let you go to sleep during the movie. It's a very short movie. But we've put some deliberate errors in this video clip and just allowed the decoder to recover. But they've been the errors have been inserted in different parts of the picture data. So I'll just let that run so you can see the effect. Didn't say it was an interesting movie. So the title of the file gives it away. Sorry about that, but I was going to ask you where you thought the errors might be. But I'm sure you would have been able to tell me because, well, tell me why. Well, the first case. Well, I'm telling you the error was in the eye picture, but how would you have been able to deduce that?
Because it was a very big one.
Yeah, it took a long time, right? If eye pictures occur every half a second or so, then if we knock out some part of the eye picture, then that's used to predict everything else in that group of pictures. So it's we have to wait for the next half a second, 3/4 of a second before the error gets erased. And the next one, of course, is in a P picture. So it's a relatively short interval because I don't know which P picture, but we just have to wait for the next I picture to come along to erase it. In that case, B picture, just one frame, right? I'll show it one more time since I've gone to the trouble. Alright, so with an I picture, the error persists for a substantial part of a second. P picture, shorter period. And for a B picture, a very short time. Just one frame.
Picture because it's happening where the movements happen.
Right. Yeah. Oh, that's true. That's an important point. It also depends on what's actually happening in the video at the time, right? If there happened to have been a scene change at the same instant, and we were we had some hangover from the previous data because it wasn't updated, it would have made a terrible mess for the time in the GOP time between eye pictures. So yeah, it depends on which data is affected, which part of the picture. If it was important parameters about the location of the array of macro blocks or something, then we might have written a part of the picture in a completely wrong part or something like that. So, let's talk a little bit about errors and loss. There are different types of transmission errors. They can be random bit errors that occur just due to say, completely isolated signal impairments or random thermal noise or something will occur largely in isolation, or erasure errors are where we have a burst of errors together. So that could be something like a radio, like a microwave interference or something that occurs for a short period, but it causes a number of bit errors. Or if we moved into a poor reception area, for instance, with our mobile phone, we would get a burst of bit errors. So, as you might expect, these different types of errors would have a different effect on the media that we're decoding. These random lines are supposed to indicate variable sizes of media packets that we might want to have represented. So if we had a burst of errors out of in a particular part, we might lose a substantial part, but it might be isolated compared with these other ones. If we lost data in a packet-based system, and particularly if we lost header information, then this could be like an erasure error, in the sense that even though it's an error that might only affect one bit or a few bits, if it's in the header, then it could mean that we lose our entire packet. And the loss of sync when we're reading code words can mean that just an isolated bit error can have exactly the same effect as an erasure error. So if we consider that, say we've got this compressed video bit stream, we've got start codes, remember the picture start codes, and group of block start codes, I think, similar as the typical thing that's done. And suppose there was a packet loss which took out a large chunk of the information between these start codes, then this would mean that we would lose all the rest of that data, right? We had a start code here, we started decoding and interpreting the data here, lost a great chunk of it, don't know how to start decoding here because we don't have any synchronization point. So we just go in a loop in our decoder, waiting until we get the next start code. Now think about what happens if we have just an isolated bit error in here. Well, in fact, whether it's a chunk of data like that or an isolated bit error, the effect could be the same, because once if we've got variable length code words and so on, we could lose synchronism, and all the rest of the remaining data will be unusable until we get to the next synchronization word. So, in other words, a burst of errors or packet loss could have the same impact as just an isolated bit error because of the availability of synchronization words. So how do we handle errors or loss of data? There are a couple of options that we can think about. One is that we could try to protect against those errors. So if we make the multimedia data stream more robust before we send it, then we might be able to recover more quickly in the event of an error or a loss. An alternative or another approach we could consider is trying to correct errors when they occur. If we accept that they're going to occur with finite probability, then we could decide to try to correct them or conceal them. Right, so we detect an error and we try to minimize its impact, and we'll talk about some ways that we might be able to do that. We could also, if we're encoding and transmitting on the fly, if it's not pre-encoded, then we could have some interaction between the encoder and the decoder to try to minimize the impact of errors. And we'll talk about what that means as well. But you can imagine, perhaps, if we were having a teleconference. So the video is encoded, video and audio is encoded live. It's sending information to a decoder. An error occurs. Even if we can't retransmit the lost data because we're worried about delays, just knowing where the decoder was had experienced an error or a loss could mean that we change our subsequent encoding decisions and therefore minimise the impact, but we'll go into more detail later on. And we also shouldn't just dismiss the possibility of relying on reliable transport. Poor choice of words, but we're assuming in these first 3 dot points that the errors will occur and they can't be avoided by, for instance, using TCP reliable transmission. Why do we make that assumption? Well, we assume that retransmission requires a long delay, and at least some applications of our multimedia streaming could not tolerate that long delay. But we will investigate that in more detail, and we'll actually see that there are applications, very important applications, where we can use reliable transport. Okay. So, look, we're just before 8 and we're just about to start a new subject, so why don't we stop there as a special treat before we have the mid-semester break. Thanks for that. Thanks for coming tonight. If you could start to work on those projects, that would be good. Send me a structure if you like. I'm happy to have a glance over it to see that it makes sense, make some suggestions. And if there's anything, if you have the chance to go over some of this material, if anything doesn't make sense, then let me know. Ask a question on the discussion board would be good. Have a good break if you're able to relax, and I'll see you in 2 weeks' time. Yeah? Have a good Easter. All right. Thanks. You too.
I'm not quite sure why this is nearly full and when this is nearly full and this is nearly empty.
Yep. So just think. It's more important that when this one goes up, that one will go down, and that's because if you just think of an extreme situation. So suppose we had a scene change at a particular frame number 300. Then this requires a lot of bits to describe.
Right, the eye picture.
To describe an eye picture, right? So many more than the average number of bits. So that means that this buffer will start to fill up quite a lot. Right? Now, sometime later, when we've transferred that data across to this buffer, and this decoder is about to decode frame number 300, it's going to require a lot of data to describe that new eye picture. Right? So it's going to read a lot of data out of the buffer. So the buffer's
So
going to
we need
go
to
down
wait
quite a lot.
until there's enough space to let this frame to come in. So
Well, we can't just wait, can we? Because we've got this frame clock going here. So we've got to generate a new frame every time. So, but the way to avoid the buffer emptying is to make sure it's preloaded. It's already has some data in it before we start reading it out. That's what I was talking about earlier with my simulations, which may have been a bit confusing. So there's always something in that buffer, even when we read out a lot of data to describe an eye picture, for instance. So in that case, at frame number 300 here, the buffer nearly fills up, and at frame number 300 there, the buffer nearly empties.
So at this time, is the eye picture already in this buffer?
Oh no, it's already it's been read out.
Sorry.
No, I should have been more clear about that.
Yeah.
So this is after the eye picture data is put in,
Yeah.
and this is after the eye picture data has been read out.
Yeah, that's make more sense. And also these calculations. So I know the 240 over 4. I know what does that mean, because the rate is 4,000, and we need to send these data through the link. So I know 240 on 4, the meaning of that, but I don't know why 70 should on 4, because 70 is already in the decoder.
But I'm saying how much time do we wait after starting to to generate encoded video before we can actually see the first decoded frame at the receiver. Right? So if the receiver buffer has to be filled with 70 kilobytes, that's part of that calculation. Right? So 240 kilobytes has to go just filling up the, can't remember which way, sender, sorry.
Yeah.
So we have to have to generate 70 kilobytes of data just to go into the sender buffer before we read any out over the network, right? So
Yeah.
that's 70 kilobytes.
Yeah.
Then even though we're even after we started sending data over the network, we've got to fill 240 kilobytes in the receiver buffer before we start to read anything out and display it. Right?
But
So
the
receiver-
4,000 is a transfer rate, so
yeah,
it's the rates
But-
through this link. But
but it's also the average rate at which we're generating data, isn't it?
yeah. So I think the 70,000 bytes data is already in the decoder, in the buffer at the decoder, so it does not need to go through this link.
No, how can it already be there? If there's data already there, it's not video data that we've sent. So
So this data, this 70,000 is also sent through this
yeah,
link.
yeah.
I thought it's just arbitrary choose to.
Oh, well, no, but if you put arbitrary data in, then the decoder would try to interpret it as video.
Okay.
No?
Oh, okay.
Yeah.
Okay.
Okay.
Thank you.
I just didn't understand the function of the low pass filter in this.
Oh, okay. It's purely to smooth out the variations in arrival time as a result of jitter. Okay, so
Okay.
if the
Here.
yeah, so as soon as we get a clock, as soon as we get a packet that has a clock reference,
Okay.
we compare it with our local clock reference,
Here.
the clock signal. But the time between these clock references will vary a little bit because of jitter on the network.
Yeah. Yeah. Okay.
Okay, so we might receive a clock reference that one clock reference might be a little bit behind what we have here,
Yeah.
and the next clock reference might be a little bit in front of what we have here,
Mm.
right? And so we don't want to rapidly change this oscillator up and down
Okay.
for every single clock reference. So instead we have this low pass filter. So only if it's repeatedly in front of this clock do we make a change to the oscillator.
Okay. So
Okay.
slight variations will be handled, or not big variations.
So, slight variations will just be smoothed out,
Okay.
and they'll be due to jitter,
Uh-huh.
and only sustained changes over a longer term will be because of asynchronism between the clocks. And so they're the ones that are allowed through, and they will change the oscillator.
So what actually a low pass filter is made up of?
Oh, it would all be implemented in digital, just signal processing. So
Okay.
yeah.
Because I was thinking like low pass filter means for carrying the low frequencies, something like that.
Oh, okay. No, sorry.
Right.
I just meant that you would you would digitally filter this signal just to make sure that only very slowly changing data
Yeah.
is passed through.
Oh, okay.
Yeah.
Yeah. Got it.
Okay.
Thanks.
Well, thank you. Thanks, guys. See you. Thank you. See you.
See. Yeah.
See you later. Thanks for your interest and interaction.